Here we're told that we have air at standard conditions entering a compressor, shown in the figure below. Actually, what we're showing is the compressor tank. And we're told the volumetric flow rate coming in English units, so 10 cubic feet per second. And we're told the density of the air coming in slugs per cubic feet. That's kind of an awful set of units, but nevertheless, that's what we're given. And then it goes into this tank that has a volume of 20 cubic feet, so it's a pretty big tank. And then it leaves the tank here through a pipe with a diameter of 1.2 inches with the given density, again in slugs per cubic feet, and the speed, that's the average speed, we'll assume, well, it's told uniform, so that means it's an average, of 700 feet per second, so pretty high speed. We're asked to find the average time rate of change of air density within the tank. So this will be a conservation of mass type of problem because we want to find how the density of the air, which is related to mass, changes within that tank, and that's changing because we have some air coming in and air going out, so the density in here could be changing with time. So I've drawn a control volume to surround the air inside the tank, and I'm going to apply conservation of mass to that. So the time rate of change of mass within the control volume is equal to the rate at which mass is coming in minus the rate at which mass is going out. We'll go ahead and expand each term. So the time rate of change of mass within the control volume will be the time rate of change of the density within the control volume times the volume of the control volume. Right? So that's just, I've just expanded the mass in the control volume to just be the density times the volume. Now, the volume inside the volume of the control volume here is not changing, right? It's a rigid tank, and so you wouldn't expect the tank volume to change. Normally these are made out of like steel, for example, so that's volume is not going to change. The density of the air, however, inside that control volume potentially will change with time. That's in fact what we're trying to find here, is how that air density changes. So we can take the volume of the tank. I wrote here control volume, but it's really, that's the same as the volume of the tank. So I'm just going to write volume of the tank times the time rate of change of the air inside the tank, because what's happening inside that control volume, that's the density of the air. Okay, so the density in the control volume is really just the density of the air. So that's that term. The mass flow rate into the tank will just be what's happening over here. So that'll be the density at the inlet times the volumetric flow rate at the inlet. So the density is given here, the volumetric flow rate's there. And then the mass flow rate out is happening here, and that will be the density at the outlet times the average velocity at the outlet times the area of the outlet. But we're given the diameter, so we can find the area from that easily. It's just pi diameter squared divided by 4. So we can then substitute back into conservation of mass. I'll just go ahead and write it out. And then we can just do a little rearranging to solve for the density of the air and how it's changing with respect to time. And then now it's just a matter of plugging in the values. So we're told the density at the inlet was 0.00238 slugs per cubic foot. Slugs are a form of mass in the English system. Q in is 10 cubic feet per second. Density at the outlet is 0.0035 slugs per cubic foot. So the compressor has increased the density. The average velocity coming out is 700 feet per second. The diameter of the outlet was 1.2 inches, so you'd want to convert that over to feet. And then the volume of the tank, we're told, is 20 cubic feet. So you can take these quantities, plug them in here. You have to be careful of just one unit conversion. That's just the diameter of the outlet line. And then you can calculate what the time rate of change of the air density is within the tank. And if you go through those calculations, it comes out to be 2.28 times 10 to the minus 4 slugs per cubic foot per second. Right, so just the time rate of change of density would be like a density per unit time. So this is how the air density is changing with respect to time inside that tank. So that comes from a conservation of mass type analysis. There's nothing too tricky about it except perhaps this step here, just knowing how the mass inside the control volume changes with time, just recognizing that the mass in the control volume here is the same as the density times the volume, and then noticing that the volume is a constant so it can come outside that time derivative to isolate how the air density changes with time. Okay, we'll end the example there.